you just start recording? Like, is it recording or what?
Yeah, we're actually recording.
Okay. Okay, so everyone, today we'll be going over Lab 7, which is RNN Basics. So for this week, Professor would have covered like RNN stabilities and LSTMs and other sequential like models. So starting over, what's like sequential data? So what we've seen so far, probably like you've dealt with CNNs, and how CNNs basically work is they don't have any sense of like sequential data in sense like if you find an apple or something on one edge of a picture, it is not a different apple than an apple that you find on a different area of the image. Another thing that you would have seen are like 1D CNNs or like time delay neural networks, and how they work is that they have kernel, which gives them the receptive like ability of the data that they're looking at. So even if they are sequential, they only have like very limited perception of like what the dependencies between the data. So they're mostly used for like they're examples of like n-gram models and all of that. That's where RNNs come into play. So RNNs, they don't forget what they've seen. Like they keep track of what they learned from the first data they've seen. So for instance, when we're talking about the 1D CNNs, it's when they want to calculate something, they will only look at the data that is part of their kernel, like receptive field. But if it's an RNN, it will keep track of what it has seen in the first input. However, like as we'll like talk about it later, like the problem with the whole dependency issues. So some example of sequential data is like text, where for instance, if I say the word hi right now, whatever I say next is somehow dependent on what I said before. There's also examples of audio, speech, and then you have video, which is again, even though it's multimodal, it's still temporal, because even though you're seeing like images and audio, they're still dependent on time, where what you see now is dependent on what you've seen before. And any other time series data like stock price, daily temperature, and so on. So starting off with data modeling, the type of data you'd see is like one-to-one, where you have the same number of input, and then you are also predicting the same, for that input, you're predicting the same label. So for example, here it's an image classification where you give it one image and it goes through the network and it will give you one label. And then you also have one-to-many, where if you give it one input, you're expecting like many prediction. Like for instance, in image captioning, you give it one image, but you're expecting like multiple like words to be outputted. Another example could be like something like like poem generation, or something like in large language models where you give it like one word and you expect it to like fill in the blank and all of that. And then you have many-to-one, where you have so like here we have sentiment analysis, where you're going to be giving it different words. And for all of those words, it's going to take into account all of them. And then it's going to give you one label, which is many-to-one. You also have many-to-many, which are the most like commonly used in like large language models. And like here you have machine translation, where you give it a certain amount of input and you're expecting also like similar amount of tokens. And then here we have object tracking, where for every video, like you're expecting like an object that is being tracked for that video segment. So that's many-to-many. And then you have recurrent neural networks and how they differ from other neural networks. So why they're called recurrent is whatever you see in the current input and what you've seen before, it's like basically the same, is the same network that's been repeated all over and over again. And it keeps track of what has been, what it has learned from before. So you will see how backpropagation is done through time, which we'll cover in like coming slides. So before we get into how exactly like recurrent neural networks would work and how you'd like unroll them, you cannot just pass in like literal strings, because we're like dealing with text prediction and text generation task. So how you usually have text is like it's in form of strings, but you want to do like mathematical like stuff to that, and you can't do that to literal strings. So one method is one-hot encoding, and how that usually happens is like you have a dictionary of like you have an input, you have different words, and each word is in a dictionary. So here we have "never gonna give you up," which is like a song lyric, and you have 5 different words in your dictionary. So let's say to represent the word never, you can be like, okay, if it's 1 in the first index of the 5 different indices, it's gonna be representing the word never. And let's say for gonna, you'll probably be like, okay, you'll turn off that first one and like use the second index for gonna and all of that. But the problem with like one hot encoding, as you'd realize, is like if you're dealing with more, it depends, like the way you represent this data is dependent on how many words you'd have in your dictionary. So it's like you're dealing with very high dimensional data. So it makes computation really complex. So that's where like word embedding comes into play. And how word embedding work is that you are dealing with similar type of encoding, but like you use denser forms to represent those. So like here on the right side, you can see that this is and word embeddings from Glove. And how this works is like, even though the words that you can see, they're represented, they are in like a compact form, they also have some sort of meaning. So like the word woman and man, and let's say uncle and aunt, like they have similar relative difference and man to woman. So they also hold meaning. But if we were doing one hot encoding, it would mostly be like not meaningful. So that's something the network would have to figure out while also being high dimensional. So what are you exactly predicting? So let's say we were dealing with our input was never gonna give you, and we were expecting the model to use the word up. So how this would work is you usually when you're using RNN or something, you output the probability distribution for all of the words that you would have like in the dictionary. So in this case, we were dealing with 5 different words, and our network is going to be like, okay, never gonna give you, and then let's see how was the probability of putting the word never again. And as you can see, like it's 0.01, and the same for gonna give and blah, blah, blah. And then if you're dealing with up, you can see it has the highest probability. So whatever your output is, it's usually the one that has the highest probability. So in this case, since the word up is the most likely word that the large language model would predict, it has the highest probability distribution. And it's the same, like here we're just dealing with like some words like gonna, give you, up and down. Like you can see both the words have similar probability distribution. So it also depends on like what the model predicts. Like it's okay to have same words that have similar probability distribution, and then like it's usually dependent on like how the memory is handled for the model to define the tie. So then going over RNN example, so this is for transcription, where if you give it an input, you will expect an output for that input. So if you're dealing with something like audio generation, where the first audio that you give, you're expecting a text for that, but we're gonna deal with like prediction and generation. So here you have your first input, and you'll have some sort of initial hidden state. So you will use those both to get the first hidden state. And then you'll notice, and then you'll notice like the first hidden state, it's also given to the next, for the calculation of the next hidden state, you're using H1, which is the whatever you learned from X0 and H0, and you're also giving it the X1 input. So all the way until HT, you'll realize that your network always has some sort of idea of whatever like it saw in H0. But as we'll see, because of like sequential dependency issues, it does kind of forget if it like sequences get really long. But at least unlike 1D CNNs, it is not dependent on just a kernel size or a receptive field. So dealing with prediction. So let's say you started with the word, like we want to predict up in this case. You will first give it the initial hidden state, which is like initialized to zeros or depend because you want to learn it over time. And then you'll give it your first input never. Using that, it will predict get the probability distribution using the hidden state 0 and the word never. And then we'll give this hidden state to our next to calculate the next hidden state, as well as our next input at Ghana in this case. And then it'll give you the probability distribution of H2, and so on until you get to what you wanted to predict. So in this case, the model has some sort of idea of what it saw even in the first the first letter, and it's going to use H4 and the word U to predict what the last word was, which in this case would be up. However, if you're dealing with generation where you don't want to stop after the prediction of the first, you don't want to stop after the first prediction, how this would happen is like the way we did for prediction. We're going to keep doing it the same way where you get the word gonna based on how you got never and, but when you wanted to get the word give, you will take the maximum of whatever you saw in the hidden state 2, and then you'll use that as the input to calculate the hidden state 3 and so on in a similar manner. And every time you want to generate, you will take the maximum of the probability distribution that you saw in H3 and so on. And how backprop works in RNN is every time you're going to a previous, you want to calculate the previous layer, you will keep in track of whatever loss you saw in your last hidden state and the input, and it backpropagates that way. So even though we're technically dealing with just one layer in your RNN, you can see how it seems, it depends on your time, the amount of time, like time sequence that you're using. So it comes off as like you're actually dealing with the 4-layer deep network, because that's how the losses would have to backpropagate if you want to get to the 8 zeros. And it's the same way it holds when it comes to the forward propagation, where if you want to calculate the loss, you will eventually kind of lose track of what 8 zero was, because even though it seems that's like one layer neural network, because of how things are calculated, like in a recurrent manner, you're basically losing track of what you saw in the first hidden state. Now, Shravant will cover the RNN problems.
Okay, let me begin by thinking what problems an RNN might face. The main thing to focus here is to see why an RNN is facing a problem. Well, RNN, even though they are very good sequencing models, they can remember from the start of infinity to wherever we progress the network to predict or generation or whatever task we are performing using an RNN, they're good. But the main problem that we face in an RNN are the short-term memory and vanishing or exploding gradients. And this can happen majority of times because of the eigenvalues being used at the hidden state. They might explode or vanish based on the gradients of the recurring matrix. And this seems to be a problem because if we are using RNN for infinity memory to progress in our network, which is not happening in the real life, and theoretically it is supposed to be, but it's not going to happen in real life. So that's where our architectural solution comes to play in, where we start using LSTMs and GRUs to combat these issues. Long short-term memory and gated recurring units are the solution for this particular problems. We can see that in a typical RNN, the inputs and the hidden states are taken forward for the output, but there's this modified architecture where we see a lot of strange things come into play in the architecture of an LSTM. Let me go through bit by bit. So the topmost part is called an CRU, which is like the constant error carousel, which keeps in mind that it is necessary for the network to have the information throughout our network. And this CEC will make sure that the information is not flawed and is being carried out throughout our network. And if we see the next part, there are gates which are attached to this ECE, and this plays a prominent role in our LSTM architecture because even though the history of information is being carried out through ECE, we need these gates, and I'll specify them specifically uh, what their functions are. So the first gate where you can see is a sigmoid gate, which is basically called the forget gate. This gate particularly controls what information that needs to be carried over history or forget it. So this gate estimates the information is worthy enough to be carried over for the future preferences or should have been forgotten. So this sigmoid gate is going to be performing the first state of architecture functionality to carry over the information which is necessary or not. And the second gate, we can see this small architecture where there is two functions that's being performed, one from the sigmoid gate and one from the tanh gate, where the two functions are the perceptron layer that determines if there is something new and interesting in the output, and the gate decides whether if it is worthy enough to remember and to be added on to the network for the future progress. So this is an input function which is happening right here, where the both activation layer and the input layer together perform and see if there is any information that's worthy enough to be added on as into our network, and there is an memory cell update which these two perform and carry out. And there's a final output gate where you can see the gate simply comprises with the tanh to make uh, the control output, and it decides whether the memory content are worthy enough to reporting at that particular time. So we can see that the forget gate, the input gate, and the output gate performing, there is subsequent memory update, and there is a considerate of the necessary information that has to be passed on and added on for the future network preferences. And there is also a small architecture where you can see the during this activation layer, which is called the peephole connection. And this is the raw memory information by itself, which can also be an input, which has been over in the past layers. And this, if you come to see that, this also has a prominence role because we need some information from the past which is related to our next, uh, which is related for our next information to progress along. So altogether, this is a complete LSTM unit which comprises of the input, output, and the forget, and the peephole connection gates. And this seems to be a solution for our RNN problem for vanishing gradients and the short-term memory. And GRU is a gated recurring unit is also a similar way that it functions, but we can see that for the forward and the back propagation, we go through everything layer by layer and perform the gradient descent. So we might ask, what is the training issues if we are facing in an LSTM? Some issues are, there might be a lot of noise, which RNN struggles with exploring early in training, and when the noise is present, it is very bound to happen. And two, it can be a very cold start, where there's a teacher forcing and the model is trained to use the ground truth inputs, which can lead to poor generalization during the generalization tasks. And to overcome this, we got to see how it functions on the loss of long-term dependencies. And we can see here we are trying to predict a token like Iman answered prior, never gonna give up. That was our supposed to be what the model has to be performing and predicting the tokens. But we see here sometimes when it gets maxed out, our gradient has been exploding on the layer 3, layer H2, which is the layer 3. And because of this, the model is going to start giving out gibberish. And in our example, we can see that it's displaying never gonna again, back to back. And this can be happening, this is an example of exploding gradient, but again, if there is a problem of vanishing gradient, we can see a bunch of gibberish being produced, which are unrelated to the next token prediction or or generation or any task that we are performing. So what can be a solution for this? Even though we are trying to implement our uh, LSTM, which is supposed to be covering the drawbacks of the RNN, we are still facing some problems during this lack of exploration and the cold start. And for this, we will see the long-term dependencies may be reduced or lost. And in order to overcome those, we'll see how attention mechanisms comes into picture. And this, you guys will see this in the later lectures. But to give a small hint, the attention mechanism is a highlight that highlights the limitations of RNN in the long-term dependencies. And these models focus on the most relevant parts of the sequence, making it more effective in the long range dependencies. And this is very important because we can see a lot of information being lost or being exploded. The gradient being lost or being exploded in our LSTMs or RNNs. And these attention sequence models are prioritizing what information that is necessary throughout our network operation, and these attention mechanism models preserve it until your end task and help you figure out what is necessary for whatever task you're performing. And we can see that there's a small dropout in the sequence models, which can also help in the overfitting, and the basic generalization techniques of using dropout can be really, really effective and operative in our RNNs. So just to discuss a few different types are a naive dropout, log dropout, or variational dropout. But these dropouts are necessary, especially when we have exploding gradients. If the model is overfitting, we can see that the dropout plays an important role in maintaining the regularization technique for the RNN. So yeah, that brings us to the end of our recitation. We still do have a notebook which has been recorded and which helps you to run through the basics of an RNN and LSTM model. And we would encourage you to go through the notebook and run through the notebook just to make you familiarize with an LSTM, which is a small hint, it's going to be on your homework trays. So it's a good exercise for you guys to get familiarized with it, and it's going to pop up in the future homework, and you guys are going to be familiar with it beforehand. So by that, I'd conclude our recitation, and all of the materials will be posted on the website as soon as this recitation is done. Thank you.